Hi, I'm Dr. Courtney with USAFA's Quantitative Reasoning Center. This is one of my favorite deer rifles, and I can remember lots of memorable shots and exciting situations. One of the things that I'm a little embarrassed about is that I missed 9 out of the first 10 deer that I ever shot at when I started deer hunting. That was because I underappreciated the importance of practice. Once I learned to practice efficiently so that I knew where every bullet was going to go, I started killing lots of deer. And there were some streaks where I'd hit 10, 15 deer in a row without a single miss. The same thing is true regarding the importance of practice with respect to Calculus 3 graded reviews. If you practice the homework problem sufficiently so that you really do know and have a confidence level in your skills, you're going to have a good idea what the outcome is going to be on every graded review. I also like rifle trajectories because rifle trajectories, bullet trajectories, are an important example of the real-life application of parametric equations. So are missile trajectories and satellite orbit computations are also very important examples of parametric equations. Okay, we're having a look at section 13.1, number 38, and it says to find a vector function that represents the curve of intersection of two surfaces. So what's the big idea? How do we identify or interpret the most important things in this equation? Well, we have two surfaces intersecting, and we want to find the parametric vector equation of that intersection. And then the D step, or we need to develop our plan for the problem at hand. How are we going to solve this problem? What intermediate steps, what sequence of steps are we going to use? So first, let's consider the projection into the XY plane, and so let's make our plan. Write parametric equation for x of t and y of t. In other words, both of these curves exist in 3 dimensions, and thus their intersection exists in 3 dimensions. So our final answer will be a full 3-dimensional vector equation, x of t, y of t, and z of t. But we can attack this a little more simply if we first think about, okay, let's just think about z equals 0, what's happening in the xy plane, and then once we describe the projection in the xy plane, then all we need to do is add the 3rd dimension to the vector parameterization. So then we add z of t. All right, so now we're to the evaluate, or you might say execute stage of the idea problem solving format. So let's think about what we have. We have a paraboloid, and the paraboloid is given by z is equal to 4x squared plus y squared, and the paraboloid intersects the parabolic cylinder, and the parabolic cylinder is given by y is equal to x squared. So before we go and think about the projection in the XY plane, we might, now I'm not the best at drawing three-dimensional sketches, and you're probably not either. But at least we want some kind of three-dimensional idea so that we understand the spatial aspects of what's happening in the problem, and we don't just turn this into formula roulette. Alright, so we have this paraboloid. So if we draw three-dimensional axes, and why don't we go ahead and draw our picture over here. So we'll call this the x-axis, this the y-axis, and this the z-axis. And let's think about that paraboloid. Well, in the zy plane, x is equal to 0, and this is just z equals y squared. So that's just a parabola. Now, in the xz plane, it's y equals 0, so it's z equals 4x squared. So that's a parabola as well. But since that parabola has the coefficient 4 out in front, it's rising more quickly than the parabola we've already drawn. So if we think about maybe just helping us visualize the xz plane here by drawing some dotted lines, we have a parabola in that plane as well, but it's increasing a little more quickly. And then the cross sections of this parabola are elliptical. For example, if you think about the cross section where the plane, say z equals, oh, pick a number, z equals 4 would intersect it, right? That's going to be an ellipse where you'd set this equal to 4, and then you get x squared plus y squared over 4 equals 1 after a couple steps of algebraic simplification, and that is an ellipse. So this is kind of what the cross section looks like. But we're not interested so much in the intersection of a plane with our paraboloid. We're interested in the intersection of the parabolic cylinder with our paraboloid. So this paraboloid has these cross-sectional ellipses going on. Alright, so let's give some consideration to what our parabolic cylinder looks like. Y equals x squared. Well, the cylinder y equals x squared doesn't depend on z at all. So it's completely independent of z. And it's, well, in the xy plane, it's simply the parabola. And maybe it would be best to do this in a little different color. It's simply the parabola y equals x squared. So this, we're pretty much thinking about the xy plane down here. So y equals x squared is going up like that and up like that. And that's where this parabolic cylinder, and the parabolic cylinder is coming up kind of like a curved sheet of paper out of the xy plane, something like this. Wonder how easy that is to see on the video. So that's, you're looking at the intersection of these two situations, these two surfaces. So in the xy plane, you're basically talking about z equals 0. So you're looking at y equals x squared just in the xy plane. So when we want to think about our projection into the xy plane, all it is simply parameterizing a parabola. So how do we parameterize a parabola? Well, there's a couple of ways to do it, but I usually encourage students to try and parameterize things like powers and polynomials in a way where you only end up with integer powers, because things end up a little bit simpler down the road. So let's just let x equals t, so then y is equal to x squared, and you just substitute in, so y is equal to t squared. So you can usually just pick one of your coordinates when you have a conic section, and let that coordinate be equal to the parameter t, and then your other coordinate would depend on the first coordinate just by substituting in t in the usual way. And this doesn't perhaps work for every imaginable situation, but it works for lots of situations that are likely to come up. So x equals t, y equals t squared, so x of t equals t, y of t equals t squared. And by handling the projection into the xy plane, we've essentially figured out that when you think about r of t as a vector, where the first term is the x component, the second term is the y component, all we have really left here is the z component. And now we've already expressed x in terms of t and y in terms of t, and we know that this equation has to be true as well. Now we can substitute in the x and the y so that z of t is equal to 4x squared, well that's going to be 4t squared plus y squared. And this is where we need to take a little care, because y is t squared, and now we're squaring y, so this would be t squared squared, so z becomes 4t squared plus t to the 4th power. And we need to make a little more room for our final situation. So 4t squared plus, and when you square t squared, you get t to the 4th power. So this is our vector parameterization with the x, the y, and the z components. And that completes our evaluation or an execution of the plan that we developed earlier. So now we need to assess. So how would we assess this? How would we be completely certain, or how do we gain confidence that our answer is correct? Well, if we used one of our computer algebra systems, say Mathematica or MATLAB, or if we used a three-dimensional graphing tool, for example Calc tool 3, and if we graphed both of these surfaces along with our vector curve, and if we could see that the vector curve was along the intersection of the two surfaces, then we'd have great confidence that we'd done it correctly. So to assess, we'd simply graph it.